All right, so I'm not entirely sure what the copyright is for a video to show a book. So this is the second dimension. We'll just call it an advertisement then. No one book is going to have all of the information. So we're just on Amazon. We'll probably get one of the textbooks for the class, and then I'll provide or show some of the hard copies that I have already. And with most of the standards going, or the ASME Y 14.5 2009 being the standard we're referencing, we're moving into 2014. They're already developing standards for 2018, 2019. It's just a matter of the progression. So it's getting kind of that point of arguing over, do I put a period or a semicolon here, and how am I going to make this statement? It's down to that fine tune. So this is one of the handbooks, and then we'll probably jump over into the precision machining textbook, and refer to that as our general information now until we actually adopt a textbook. All right, so we're going to kind of scroll through. This is the Kindle version, and there is still a lot of information. Don't really need the preface. Kind of nice that they put in some of the abbreviations and nomenclature that they use. And as you go through on the abbreviations, this also is pointing to the ISO standard, which has direct correlations to the ASME standard. And at the end of the day, we need to have that common worldwide language that you look at the print, you may not be able to make out the notes, but you should be able to read the symbology. All right, so some of the symbols then that we're working with, going to start with, and these are in no particular order. So when we talk about form and profile and orientation and angular and all those fun things, they are grouped into their segments. So the ones that I'm focusing on are flatness. We have the flatness, straightness, roundness, and cylindricity. All right, so those are the first four that we're going to concentrate on, mainly because they establish the rest of the controls. Right? So as we build in and we establish a flatness, then we can have parallelism, then we can have perpendicularity. And usually that first form is what gets the A datum. We recognize it for its in its selection as having value, being able to approach it, and we'll go through some more of those attributes. And then some of the, well, considering this is 10 years old, I'm not too worried about new and different. So let's see if I can, oh, it does do the highlighter, good. Okay, so my screen resolution is not going to let me jump too much. How about a full page? Single column, auto fit, maybe not. How about an F11? Okay, probably should have figured that out before I started the lecture. I'll get a little bit more on that screen. All right, so suitability of a workpiece. We're back to that scope of work, foundation material. If we just have a block and it's going to sit on the table, and other than aesthetically it needs to be a prismatic shape, then we don't really care. Make it this size and make me 100 of them and we're done. And the tolerances are pretty much wide open. The flatness, the parallelism, perpendicularity, doesn't have any interior geometry. We don't care. So suitability of a workpiece for its purpose depends on its inner properties, material, inner discontinuities, shrink holes, inner imperfections, segregations, and on its surface condition. The surface conditions comprises the properties of the surface border zone, chemical, mechanical, and geometrical properties. And then they go on with the chemical, nope, I don't want that. The chemical and mechanical properties are chemical composition, grain, hardness, strength, inhomogeneities. I hope you have trouble with that one. The properties of the surface border zone may be different from those in the core. All right, so grade 8 bolt. You have a surface harden and a soft center. Right? If you get down to it, the first, you're taking a hacksaw to a grade 8 bolt, you're going to knock all the teeth off going through that first, 30, 30 second, 20 to 30 thousandths of material is going to be really hard. You hit that inner core, well, the two outsides of the cylinder are still going to be pretty hard, but everything inside is going to be pretty soft. All right, so part of that is how we want it to bend, how we want it to break if it fails. All right, so depending on geometry, depending on the purpose, we may have surface treatments. We may try to make it hard all the way throughout, and we may want it soft all the way throughout. We just have to think about what its purpose is, and that comes down to specifications. All right, so the geometrical properties defined as deviation from ideal elements are features, and that's one of the things that we can correlate over to our SolidWorks application. Is when we're creating features in SolidWorks, they're really, most of them, I would say a large amount of them, are going to be features that we would consider adding a tolerance to. And then geometrical ideal elements, the features, are parts of the entire workpiece, surface, have geometrical unique nominal form, planes, cylinders, spheres, cones, and tori, so donuts. They can also be derived as axes, section lines, generated lines, lines of highest points, edges, and then the deviations are size. So if we just put a plus or minus tolerance on it, the part is, we take a pair of calipers, we take a micrometer, we measure, whatever that dimension is. It's either accepted as being within that range, plus or minus 5, plus or minus 10, or it is rejected as being too large or too small. Form deviations, back to the flatness, to the circularity, cylindricity, is it's not very flat. All right, there's waves in it, or surface conditions come in. Orientation, usually interior geometries, locational deviations, so that positional tolerance, how those interior geometries are placed in the within the part. Waviness, roughness, surface discontinuities, and edge deviations all are leaning towards manufacturing processes. The process that was selected is having an effect and is going to affect the inspection, the acceptance of the part. So the breakdown of our surface condition, we have that boundary layer, upper and lower boundary layers, and each of those possibilities, each of our deviations can pass or fail that part. So when you get into the chemical and the composition, mainly the physical is the hardness, the residual stresses, and the grain. So we often think of wood having wood grain. Well, when aluminum is extruded, you get a grain to the material. When you have the bars coming out and you see that butter coat of, the oxidized surface, that technically has some grain to it, and we've aligned those stresses within the bar. Probably the most notable example is going to be like a 304 stainless. Nice, fairly easy to work with material. It has some hardness to it. It has good wear resistance, but it also has a lot of internal stress. So if you were to take a 1-inch thick piece of stainless steel and machine 10 to 20 thousandths off of one side, there would be a possibility that just taking that scale, just taking that from the foundry, from the manufacturer off, is going to change the tolerance. Is it going to be straight along that linear, or is it going to be able to maintain its flatness? When you machine, and we talk about restrained state and free state, 304 especially, if the material is a little on the thin side and a large plate, and you remove a lot of material out of the center, it's going to turn into a banana. You release it from the clamps, it's going to be either banana or pretzel, take your pick. Right? We have to either stress relieve it or manage the machining process to where it doesn't, those processes don't impact as much. All right, so then back to review of, and then they used a cylindrical part, but axes, spherical, cylinders, just some of the items that we would be interested in. And so we get into those deviations and definition. So I like this because not a lot of the standard textbooks go into why is this an issue? Why would this fail? And so having kind of this foundation material is important to me. The size deviation then is the difference between actual and nominal size, and then some more definitions. Form deviation. Okay, thank you, Kendall. Form deviation is the definition of a feature or deviation of a feature, the geometrical element, surface, or line from its nominal form. All right, so it's has that wave in it. It has some angle to it. And then if not otherwise specified, form deviations are assessed over or along the entire feature. So where we talk about flatness, when we talk about straightness, it's kind of one segment, one section. We kind of pick where we want it to be straight, or we identify where we want it to be straight, and then we're only measuring pretty much along that line. The flatness says that I'm going to try and get my indicator to reach every point on that surface that I can reach and be able to get a measurement for it, or at least enough of them that I have an average of the surface. And then orientational, from its normal form, orientation related to one or more datum features. So basically, as things shift or move within the part, we can have the orientation, locational, still deviation of the feature, surface lines or points from its nominal location, and also related to datum features. Let's see what else. Originated similarly as size, form, and orientation. Waviness is mostly periodic irregularities and spacings. So kind of that wave, and we're still staying within the tolerance zone, but when you are milling with a standard end mill, if you go too fast, that epicycle has a lot of space between each of the turns. If you're going fairly slow, it has the ability to drag a chip underneath it and scratch the part while it's clearing that chip. So kind of the washing machine effect. So we want to kind of be aware of those deviations. And then on we talked a little bit about roughness last time, where just in the process of machining, depending on selections we make, criteria we set with the machines, is also going to affect. So roughness and waviness are very, very similar. And then surface discontinuity, cracks, pores, or laps. So one of the things that I would encounter pretty regularly is, I'm trying to think if it's polypropylene or polyethylene. I know the peak, which is polyester ethyl ketone. You'd be machining along, and all of a sudden there'd be a hole. It might be the size of a small ball bearing, and sometimes it was enough you could get a fingernail to catch on and start it. Natural inclusions in the material come into those into that type of discontinuity. And then we get to edge deviations. Talk to any machinist, one of the obsessions is burrs. If you do a machining process as that tool rolls over a feature, rolls over a hole, rolls over an edge, it's pushing that material and it's creating a burr. Those burrs will be good for anywhere from a couple thou to 10 thousandths, depending on the material. And it's going to affect your end product. So deburring and being able to break those edges and not have it affect the next machining operation, whether it's setting it down on parallels in the vise, or I'm taking an edge finder and running it up against a burr instead of the actual surface, and it makes a locational deviation because I didn't check to make sure that I had the edge properly prepared. And then some classifications, depths. All right, that might be good on the other surfaces. And then they go a little into the forms, where It just kind of has some radius to it. Maybe the part rocked, maybe it pushed. The waviness, the roughness. All right, so very similar. Could even say it's a matter of frequency or something that happened in the material. And then another type of roughness where it was part of the process. Crystallization or corrosion. So I brought in my V blocks that were made in 95 or 90. I have to look at the date on the bottom. The antique V blocks, and they have a little bit of surface corrosion on them. That is enough to change the tolerance of and potentially change, any of the inspectable features. And then crystal structures. They didn't really elaborate on that one, but I would think that would be still along the lines of corrosion, that you're having an oxidation, you're having something build up on the surface of the part as part of, maybe that's crystallization, and crystal structure might be interior to the part when they're getting down to the metal matrix and those. So anyway, what was the last one? And then superposition, the actual surface just has all that, kind of looks like a fractal. All right, so key phrase here. It is impossible to manufacture workpieces without deviations from nominal size and shape. All right, even on the best day with the CNC warmed up, room temperatures, everything nearly the same, the tool wore a little bit more on the last part, and it's wearing a little bit more on this part, and it will continue to wear on the next parts. We're not under the same cutting conditions that we were under the first part by any means. And so workpieces always have that deviation. And so that's where we're getting into our tolerances. Whether you look at a print and it's all just plus minus tolerances and it doesn't have the same effect, or it becomes critical that we have flatness, that we have perpendicular, that those things start to drive the end conditions of the part. The other thing that would be of consideration, and I look at the too large, but one of the things that when we start talking about like tolerant zones and getting further into the references, that if we had a really large surface plate, we have a 6 foot by 4 foot, and the thing's got to be 12 inches thick, and it probably weighs a couple tons. I mean, it's a huge piece. How do we know that is flat? Well, and then we take a piece of aluminum that we want to make 1 inch thick, and we buy it 1 inch thick, but then I set it down on that plate and it rocks. Well, all of that granite surface plate still has microscopic porosity. We have dust settle on it. We have the burrs on the aluminum. We have that internal stress in the aluminum. Just the process of setting it down on the plate and seeing it rock tells us something about that material. So we have to decide if it's usable. And then their point of attempts are made to keep the deviations as small as possible. Then the production costs go up, and we're not really going to sell that many. It may be the most perfect part, but if it's $1 million a piece, who's going to buy them? All right, so market forces, our ability to produce things in a timely manner with those variations. We want to define the workpiece to what it needs to do as the designer, as the machinist, as the technician doing the inspection. You want to be able to communicate across all of those levels and make sure that everybody's reading the same symbology, the same functionality. So one of the other books, the Geometric Dimensioning Tolerancing Handbook, made a couple of good points that well, I just had a brain skip on the economic production. That okay, I have to come back to that one. So what we're getting down to is in the scope of work, we set the specifications, we develop the timeline. Marketing says this is how much we can sell it for, and engineering says we can't make it for that. Well, what can you make it for? No, we still can't sell. That's part of the communication as well. These tolerances have to drive and do the stack ups, and so that we find the place where those two curves meet. Completely tolerance drawings. All right, so every feature that we put a dimension on, whether dimension carries a tolerance or not, one of the things we're going to look at on the SolidWorks side is that I created a template probably a year ago now. It was it might have been the fall of 2017, and I did not include a tolerance chart. The do not scale this drawing and the standard tolerances, unless otherwise specified, are 2 decimal places, or plus or minus 10 thousandths, or plus or minus 15 thousandths, whatever your industry standard would be. 3 decimal places, plus or minus 5. When you get into 4 decimal places, you have a choice to make. Do you want to make it so tight and so critical that if you need it, sure, plus or minus 2/10 of a thousandth. That part just got way expensive, right? Giving plus or minus half a thou isn't a whole lot better, but it is quite a percentage gap. Going to plus or minus a thou, which is what I would put on most of my general production, 4 decimal places, shows that it's critical. Hold this tolerance as tight as you can, but I'm not quite an order of magnitude from the plus or minus 5 thousandths, but I'm in a zone that makes it manufacturable. And then if I need something that needs to be plus or minus 2/10 of a thousandths, I'll put it in. So your company, your designers, your engineers need to sit down and have that conversation of standard tolerances. If I just put a dimension on it, I don't put a plus minus or a limit or any of those in, what is it going to read as? All right, so general tolerances should be equal or larger than the customary accuracy. So if everybody's running around with a tape measure, 12 foot, a 25 foot tape measure, and we can say, wow, we can read to 16ths. Well, I would like to be at a 32nd, so I want you to guess between those two numbers, but that's going to drive everybody crazy. How do I know that? Because I did that. And that was a conversation of, I should be able to hold to 64ths. Well, my tape measure doesn't read to 64ths. It reads to 16ths. So it needs to be plus or minus a 16th. Well, then it's not going to fit. All right, so where is the trade-off of how do we manufacture this? How do we get you the tools in your hands that you can actually measure this to the level versus our customary accuracy? Let's see. Larger tolerances bring no gain. That's kind of an important, I'd say an important one, because at some point you're going to reach that crossover point that, basically you're just slapping things together. There's really not going to be much consistency in the parts. You can go through quite a bit. So if a machine is capable, and I work into my process, I tell the people that I'm training and the people that I'm introducing to machining that I will try to hold plus or minus 1 tolerances. So that is part of my thought process. So that is what I'm thinking in. It's not something that is a higher expectation. If it goes either way, I get a little bit over, a little bit under, I make the decision. I don't necessarily take another cut on the part, but I want to know why that part came out 2 thousandths high side or 2 thousandths low side. As long as it's in tolerance, I'll move on. But the being able to hold plus or minus 1 becomes part of the process, that when I get a print that is covered in plus or minus 1s or 2s, thousandths, then it's just something that I can deal with. And then when I see the prints that are coming in at the plus or minus 2/10 of a thousandth or plus or minus 5/10 of a thousandth, then I'm taking and stepping up my game a little bit, a little more caution, a little more care, and being able to pull those machines in, know what my stack-ups are, and be able to produce that part. All right, so this is from the manufacturing side. So as a machinist, I look at the print and go, wow, that's going to be difficult, but as long as it's quoted enough time and I can think through the process and I have the tools that'll do it, I can make this. So the dealing with large deviations can be as difficult to work with as small. So you need to have some common sense there. And then no standard available, and a company standard is in place that needs to be explained on the print, or somehow common knowledge that isn't common, communication by telepathy that goes over everybody's heads. Those are common practices in industry. Putting a note on the print that maybe half the people will read, that is still not really enough. It needs to be advertised and go through that process. So general tolerances in or near. Thank you. And let's see, and then that must be smaller, have to be indicated so as called. All right, so I don't want to get any further into the symbols with this one, and so we'll revisit these. Like I said, I don't want to sit and read the whole book, but the first couple of chapters here, setting that stage for know your material, know your machines, know the people and the resources that you have to produce these parts, and and make good decisions. So let's get out of this for a second, and I will go back to library. So I'm going to jump back into the precision machining. All right, so we kind of looked over this last time, and same thing. This is the NIMS precision machining technology. So if you have that book from a previous class, then you can kind of reference back to it. But these are those general descriptions. These are not going into nitpicking detail with lots of examples. So really the definitions of our datums and going through through the buildup, datum kind of comes after form tolerances. And so the in our process, the datum is a feature, so something that you can touch. So there is the imaginary, and that was one that the GD&T handbook brought out that I think was an important concept, is that when you're imagining these tolerance zones, it's just that imaginary. Until you have a part in front of you that you're measuring, you're inspecting, you're seeing what those conditions are. On the design side, it's just what's inside your head. It's what's inside the collective imagination of the design group, of the engineering group, that sets what those tolerances need to be. Once I have the part in front of my hand, then I can say, yeah, that's real. I can touch that surface. I can put an indicator on it. It's something that I can measure. But I shouldn't have to do math. All right, if I have to split the difference and make the calculate something that is a center line or a center plane that I can't physically get to, that's not going to count as a datum. So you have to distinguish between the reality and the imaginary within these tolerance zones. And I think from a theory standpoint, just teaching GD&T as, hey, here's a form tolerance, here's our profile tolerances. It's kind of that grasping the whole imaginary portion of it versus the reality and making the connection between those two. That's where a lot of the difficulty comes in. All right, so let's see, reference point called a datum. Only some features require a datum. Well, it comes back to we look at the part and what is it that we want to control. So that's part of our imagination too, is this is critical. All right, if I can get away with plus minus dimensions and have fairly open tolerances, I don't need to go any further. I need to understand that I have these tools available, that I can utilize the GD&T, and I can also overdo it. And I can make the part very difficult in its symbology to understand, difficult to inspect, and also raise the price trying to control too many things or control the wrong things. Right, so some of the symbology, let's see. We'll talk a little bit in lab about the datum planes, but primary, secondary, and tertiary. Those are terms that hopefully you recognize or have heard before. And what that means is that our primary will sit on 3 points, regardless of that roughness, regardless of the waviness. That when we set a flat object on another flat object, it's sitting on at least 3 points. If we're building an inspection fixture, we probably want to have it set on 3 points to inspect from. Right? It just kind of depends on, again, what our goal is and what we have available. The secondary is going to contact typically a perpendicular plane, perpendicular surface at 2 points. So we're reducing the contact by 1 each time we go through one of these datum planes. Right? So we go from 3 on the primary, 2 on the secondary, to 1 on the tertiary. So that's how we're locating it in 3D space. Right? And then when we talk about the application of additional form and profile tools, tolerances, that we're going to want to think about those in terms of how much they should be above and beyond, so that the controls do not supersede each other, I guess is a way. They don't get ahead of each other. All right, so when we're picking our most important part. The feature control frame is what we're generating the symbology in. So the datum gets called out with the ABC. It goes A through Z, and then if it keeps going, you start with double A all the way through double Z. Let's see if I can remember off the top of my head the 2 or 3 that are not used. I want to say I and O are typically jumped over, all right, because of their confusions with 1s and 0s. I need to look at that one again. I know there's at least 2 or 3 in the lettering sequence that will bypass, right? And then it would start at triple Z's. So if you manage to go through 52 datums, that's a complicated part. I don't know that I want to see that one. So the feature control frame then is how we're going to apply the tolerances to those datums, to the features, to the features with those datums to gain control over the parts. All right, and then finally we get to the tolerances. So our form tolerances, that's where we're going to concentrate. So I'm going to kind of stop here with the flatness, the circularity, cylindricity, and straightness. And did they get straightness in there? No, I don't see it. So mainly these are our foundation tolerances. We say this is going to control and build up and take us to the next level. So our first level is the form. How are we going to control flatness or cylindricity, or do we need to control flatness and cylindricity? If it's straight in one direction but not quite straight in the other direction, is that critical? Some parts we may know have that deviation, have those kind of intrinsic problems with the material, but if we can align it in such a way, we can make it manufacturable, reduce the cost. So the circularity and cylindricity, we'll take a look at those. And basically, we're talking about roundness, the round parts, and to a certain extent, cylinders are going to be a lot easier to measure than cones, and cylinders are going to be a lot easier to measure than spherical, and spherical radii, spherical diameters, those types of things. So we need to kind of work up and into the rest of the tolerances with a good understanding of the form tolerances. All right, so I think we'll got a good stopping point. We'll pick up with the SolidWorks.